Lesson, we're going to learn about molecular geometry and how electrons arranged around the central atom will dictate what shape molecules can take. We're going to start by looking at this POGIL, which talks about Lewis structures. And when you draw them on a piece of paper, you're making a two-dimensional representation of those atoms. But in reality, they are three-dimensional. And so the true shape of a molecule is important because it determines many of the physical and chemical properties for the substance and whether or not those reactions will take place. So we are going to learn how to predict molecular shapes based on a Lewis structure. So we have some Lewis structures here. We have this molecule, which is H2CO. We have a central atom of carbon, double bonded to an oxygen, and then some hydrogens on either side. What we are noticing is that there are three electron domains. What they are referring to is this is one domain between the central atom and one of the bonded atoms. Here's a second electron domain. Here's a third. So these are around the central atom. Around the central atom, there are three electron domains. And of those three electron domains, all three are bonding, meaning there's an atom attached to the other side. There are zero non-bonding, otherwise known as lone pairs. Here's another example, BeF2. Be is in the center, and if we look at that central atom, there are two electron domains coming off of that central atom. So two electron domains, both of which are bonded to atoms. So two bonding domains and zero that are there are no non-bonded or lone pairs around that central atom. I recognize there are lone pairs over here, but we're talking about there's no lone pairs on this central atom. CH4, taking a look at our central atom, there are four electron domains, all of which are bonded to other atoms. There are no lone pairs, no non-bonding pairs. NH3, here is our central atom. It actually has four electron domains, right? It's got 1, 2, 3, but here's our fourth. So of those four places where we have electrons, three of them are bonded to other atoms, and one is not bonded. So that's our lone pair right there. Here we have water, H2O. Our central atom has 1, 2, 3, 4 total electron domains, two of which are bonded, two of which are not bonded. Here we have CO2 around our central atom. We have 1, 2 electron domains, both of which are bonded to atoms, and there are no lone pairs around that central atom. We'll come back to this column here in just a bit. So explaining the difference between bonding electron domains and a non-bonding electron domain, non-bonding electron domains are the lone pairs. Right? So that's two electrons only attached to one atom. A bonded electron domain is it's two electrons that are shared between two atoms. It's basically a covalent bond. And that covalent bond can be a single, a double, or a triple bond. So now we're going to start to take a look at these electron domains and recognize that electrons are negative particles and don't really want to be near each other. Okay? So we're going to circle the correct word or phrase to complete the sentence. Pairs of electrons are going to repel each other because they're negative and they're not attracted to each other. Two bonds on the same atom, right? Two bonds on the same atom will try to get as far from each other as possible because two bonds, right, are made up of electrons. So we're saying two pairs of electrons, right? Two bonds, each bond having a pair of electrons. They're going to try to get as far from each other as possible. A lone pair of electrons and a bonded pair of electrons, doesn't matter if those electrons are bonded or if they're bonding two atoms or if they're just a lone pair, they're still going to push away from each other as far as possible. And so this leads to this concept of VSEPR. VSEPR, valence shell electron pair repulsion. It's a theory that helps you predict shapes of molecules and is based on the premise that electrons around a central atom will repel each other. Okay, they will repel each other. Electron domains are defined as high electron density, where there's an area of a lot of electrons in that area. And they can either be bonds, single, double, or triple, or they can be lone pairs of electrons, right? So really what we're saying is that all electron bonding domains, whether they're bonded or not, they need to be positioned as far apart from each other in three-dimensional space. And that's what's been tricky, because so far we've only been talking about these in 2 dimensions. Okay, so this is important because the electrons that we are referring to are the valence shell electrons. Those are the electrons that are on the outermost part of the atom. In the VSEPR theory, what's repelling what? Well, electron pairs are repelling, electron pairs will repel other electron pairs. Okay, so this is just a little bit repetitive. Electron pairs. All right, so it turns out that we can have these three-dimensional molecular shapes. There are 5, and you are going to have to learn to recognize all 5 of these. The shape can be linear, trigonal planar, tetrahedral. This one is trigonal pyramidal, and then there's bent. Okay, and so what we see here is the tetrahedral. There's a central atom with 4 atoms coming around it. Tetra is a prefix that means 4. Linear, of course, is linear. You've got 3 atoms in a straight line. That's sort of fairly evident. Trigonal means 3, right? So we have a central atom with 3 atoms around it. This is all laying in one plane, which is, again, hard to see on a 2-dimensional piece of paper. But this is contrasted to a trigonal pyramidal. Here we have a central atom with 3 atoms bonded, but because this one has a lone pair attached to the central atom, that lone pair is going to push down on all the other bonded pairs, causing these to be bent towards each other, and it looks like a very squat little 3-sided pyramid. Then we have this bent shape, right, where we have basically 4 domains around the central atom. Here's a domain, electron domain, 1, 2, 3, 4. There's 4 areas of electrons. 2 of them are not bonded. 2 of them are bonded, right? So the molecular shape is bent, but it's bent because of the lone pairs here attached to that central atom are causing these 2 atoms to be closer together than they would normally be. So let's take a look and go back to the original chart. I'm recording. Give me 2 minutes. The 3-dimensional shape here, we have a trigonal with a central atom with 3 atoms coming off of it. So this is going to look something like this. This is trigonal planar. Here we have a linear molecule, and this would look something like this. In this next one, we have a tetrahedral, where we have 1 atom in the center. And then we tried to draw this. This is a little bit tricky to draw. It would look something like this. 3-dimensionally. We're trying to draw that 3-dimensionally. This next one is going to be trigonal pyramidal, where we have 3 atoms coming off of the center. Draw that one a little differently. Okay. And we're not going to draw the lone pair. Those are not included in when we draw the shapes. So this is trigonal pyramidal. The electron pair, the lone pair is not shown there, but that is what's causing these to be closer to one another. This one is bent, where we have something that looks like this. Again, it's bent because there's electron pairs pushing those down. And then the last one here we have is CO2, which is, might look something like this, right? And this is a linear molecule, All right, so those are the 5 shapes you are going to have to learn to recognize and understand why they have those shapes they are. Again, valence shell electron pair repulsion. It is the electron pairs that repel each other, and that dictates the molecular shape of the molecule. All right, that's it for now. We'll see you back in the classroom.